So let's get started. We've made it to week 6. We're still in class. There were predictions of how long we would go. I was thinking maybe we wouldn't make it to week 6, but here we are. Now, I usually start with a COVID update of some kind, and this time I want to tell you one of my favorite things as a statistician, one of the things I love most in the world is making predictions about what's going to happen in the future. And I'm actually pretty good at making predictions. And I have a pretty good track record of getting it right, which is due to a tendency that I have to only remember the predictions that I was correct about and then ignore the ones that I got wrong, and create a hindsight bias for myself that leads me to believe that I'm actually really good at predicting the future. So I wanted to start off this particular update with something that was in the Springfield News Leader, making a prediction. And what I love about predictions is we can test them to see if they're accurate. The prediction is this: a smart thermometer company predicts that Greene County could soon have a COVID-19 surge. Now, why would they say that? There's a company out of California saying that Greene County may have a surge of coronavirus cases in the next 2 to 3 weeks. So that gives us a time frame. Predictions are always so much better when they have a time frame attached to them, rather than, I think something interesting is going to happen sometime in the next little while, or the virus is just going to go away eventually. When they're open-ended, predictions don't really tell us anything. So our local transmission rate is roughly 1.02. We would use this as something like an odds ratio. What are the odds that something will or will not occur? And whenever we divide anything by itself, we get an odds ratio of 1. So what you look for in these kind of predictive models is numbers 1, or let's say numbers above 1 indicate a greater likelihood for something occurring, and numbers below 1 indicate a lesser likelihood of something occurring. So what they are saying, they keep track of anonymous data of spikes in fever. And they do stress that they're not keeping any personal data about you or anyone with these thermometers. But they are saying that there has been an increase in the number of fevers, or the types of temperatures that have been recorded here in Greene County. And it's actually all across southern Missouri. So they would predict then that based on a CDC sampling that says that 96% of cases experience fever, that this increase in fever is a leading indicator of an increase in cases. So leading indicators and lagging indicators. A leading indicator is one that comes before, and that's what we use to make predictions. So when you see a leading indicator for economic news, you would say, oh, we predict the stock market will go up or go down as a result. And a lagging indicator would be one that follows behind. The best example following COVID would be number of cases and then number of deaths. So if you see an increase in the number of cases, you would expect to see an increase in the number of deaths, but it being a lagging indicator, that would occur later on. So now you know, that is the prediction, and we're going to get to follow that over the next 2 or 3 weeks and see what happens. Like I said, one of the things I love most in the world is making predictions, although this is a prediction that I hope will not come true, but we will see. So with that, let's jump into what I really want to talk about today, which is chi-square. And I want to tell you why we use chi-square. First of all, what it is, why we use it. I'm going to show you a little bit about what the textbook is teaching us about the chi-square. And then I'm going to give you a tool that will help you to do the chi-square tests much more easily than what we are learning about in the text. So let's start with this chi-square test. It is a non-parametric statistic. Now, so far we've learned about things like t-tests, where we're comparing two groups on one scale level measure. And those are parametric tests. So ANOVA, t-tests, regressions, all use scale level data. But another important type of data that we will encounter very frequently is nominal data or count data. So I'll give you an example. Let's say we were going to throw a party. Probably not a great idea, but I've been using this example for several years, and until now, it's always been a great example of us getting together at the end of the semester. We're going to have a party, and we're going to buy everybody a soft drink, So you'll have one waiting for you, but we need to know ahead of time which kind you want. So we have 6 types of soft drinks available. We have Sunkist, Dr. Pepper, Coca-Cola, Sprite, Pepsi, and Yoo-Hoo, the chocolate drink. Would anybody vote for, I'm going to pick the Yoo-Hoo? No takers on that one, okay? We're going to have a lot of folks. Let me just, which one of those would you pick?
Oh, I don't know. I mean, Coca-Cola, some childhood memories there.
Okay, so Coca-Cola would bring back some beautiful memories for you, just enjoying that Coca-Cola flavor. Have you ever been to Atlanta or to the Coca-Cola plant, the home of Coca-Cola in Atlanta?
I've been to Atlanta.
Okay.
Not the Coca-Cola plant.
It's well worth the, whatever money it costs to go on the tour. They take you into, they show you the vault where they keep the secret formula, which probably not, but they do show, they build it up as though they're going to show you the secret formula. And but at the very end of the tour, you go into like a cafeteria, except all of the places where you might typically expect to sit to have lunch, they're all stations with Coca-Cola products from across the world. So you could get to taste what Coca-Cola would taste like in Ecuador, or some drink that is served only in Singapore. It's the local flavors, and they have them all in that one place. So that was fascinating. That was totally worth it to try those samplings from all over the world. So we have one vote for Coca-Cola. Anybody else on Coca-Cola? No. Sprite, Pepsi? You have a preference of Pepsi?
Dr. Pepper.
Dr. Pepper?
Dr. Pepper.
Okay, so we have 2 votes for Dr. Pepper, 1 for Coke, 1 for Pepsi. If we had 30 people in class, we could figure out how many of each of these types of soft drinks gets a vote. So we have 6 types of soft drinks, and one assumption that we could make would be that all of these types of soft drinks are chosen equally or chosen randomly. So if I had enough soft drinks, one for everybody, and I just put them all into the cooler with the ice and said, reach in, grab what you want, and you just, whatever's in there, the first thing you reach for, that's what you're going to drink. That would be more like a random selection. Now, if that was the case, then we would expect that each type of soft drink would be chosen equally. That's a random distribution. So if we had 30 people and we have 6 types of soft drink, we'd expect that each one would be chosen 6 times. So it's randomness. But if we had, let's say there's 60 or 90 of these, enough that people could choose which one they really wanted to drink, just based on our sample, we would say, I bet that Dr. Pepper is going to be twice as popular as either Coke or Pepsi. So we can make that kind of prediction. So what we have here are count data, or nominal level data. So you can't divide Coke by Sprite and get an outcome. It's just how many people choose each one. Not scale data, just nominal level data or count level data. Well, how do we analyze that? To determine whether the soft drinks are being chosen randomly or whether they're being chosen based on some kind of pattern. And that is where this chi-square goodness of fit test comes in. So it's a non-parametric procedure, meaning we're not using scale level data, not using parameters to estimating populations. We just want to know how well what we observe matches up to what we expect. Well, if the soft drinks are chosen randomly, we would expect that there's an equal number of each type of soft drink that's selected. But if what we observe is that we're all out of Dr. Pepper and nobody touched the Yoo-Hoo, we would say that these drinks are not being chosen randomly. There is a statistically significant difference between what we observe and what we expect. That is how a chi-squared goodness of fit test actually works. Now, the textbook will teach you all about the math, but I'm going to show you just how we would actually do an experiment like this. So most of the tests that we would be using would be parametric tests. For our purposes today, we're using this chi-square test. We'll be using non-parametric tests. This can be used with nominal data, can also be used with ordinal level data. The advantage to using a non-parametric test You may have noticed when we did t-tests, there were assumptions for those tests. So we did assumptions checks first. You would check for normality, you would check for the homogeneity of variance using a Levene's test. Those are assumptions built into a t-test. With non-parametric tests, we don't have any of those assumptions. So where non-parametric tests really shine is when we have messy data that don't match the assumptions of a t-test or an ANOVA or a correlation, we have a non-parametric alternative to those tests that we can use, so we can still do an analysis, but we have to do it in a different way. The trade-off for that is less power, which means that we're really going to need a larger sample size, and it's more likely that we will miss out on an effect that is actually there. Non-parametric tests are not susceptible to outliers if we have that violation within our data. They don't require the same assumptions that a t-test or an ANOVA would require. They're easier to calculate. In the case that I'm going to show you, it's simply drag and drop and replace, and you do this very, very simply. And the trade-off then is that they may not be as powerful. So in a case where if we had beautiful data, we would be able to find an effect. With our non-parametric tests, we may not find an effect that might actually be there. It's called a type 2 error. Now, in the example with the soft drinks, we saw 6 types of soft drinks, and so we could simply divide. We have 30 people, 6 types of soft drinks. How many should each person choose? And the answer should be 5, which causes me to think, I think I said 6 earlier, which is embarrassing. So, well, good reason not to do math in public. So if we have 30 people choosing among 6 types of soft drinks, we should have 5 each. Well, let me give you a different type of example. In this case, we're not assuming randomness, that is not our expected, but rather a good fit to some existing percentages or probabilities. So in this case, we are doing polling data, and we know the pattern that exists within our state. So on this particular topic, 60% of the people in Missouri favor, 35% oppose, and 5% are undecided. So that becomes our comparison group, our expected values. We do a survey in Arkansas, and what we find is that 58% of people favor, 36% oppose, and 6% are undecided. So what do you think? Is that a good fit to the Missouri numbers? It doesn't have to be exact, but close. So do those numbers pretty much match up? Yeah, so we would say that in this case, the Arkansas numbers are a good fit. If we were doing a chi-square test, we would say that there was no difference from the comparison group. We would find that we would fail to reject the null hypothesis of no difference. This would not be statistically significantly different. Now we do a poll in Iowa. And in Iowa we find 42% of people favor, 54% oppose, and 4% are undecided. Is that a good fit for the Missouri data? Does not seem to be. These percentages are different than what we find in Missouri. Have we done a chi-square test? We would determine that there is a statistically significant difference between the observed distribution that we find in Iowa and the expected distribution that we would find in Missouri. So we're comparing those observed versus expected to be able to make a determination about whether two groups are different. Are the observed values different than randomness? Would be one set of expected values. Are the observed values different from a known distribution? Would be our second possibility for a set of expected values. See that, right? So the textbook gives you the formulae that you need in order to calculate the chi-square. And you will get a chance to do a few chi-squares using Excel the way the textbook shows you, where you create an observed column and an expected column. You subtract those and you square them, and then you divide by the expected value, and then you add up that total, and you get the chi-square. So you get a chance to play with that. Well, what happened was I was doing a lot of chi-squares So if you go back a few years when I was working at a research institute, I was helping researchers with their chi-squares, with their ANOVAs, with their regressions. I kept doing a lot of chi-squares, and they were simple enough to do in Excel, but I was doing the same things over and over again. And I thought to myself, I said, self, this would be much easier if I just created some templates that I could always use anytime I had a chi-square setup, which is what I developed. And then I discovered that other people really liked using these templates because it was just simpler for them. So I'm going to give these to you so you can use them for this test. Another reason that I've done this is you will see how to do this in Excel. But I would encourage you, if you start doing the same types of analyses using Excel, make yourself a template like this because it can just really come in handy rather than having to set it up and do it every single time. This can be really useful. Or, in this case, you don't need to recreate the wheel. Let me just show you how I've done this. So this is, I call it the chi-square calculator, and there are tabs you can see along the bottom. I'm going to start with the green one. This is critical values. When you do any kind of test, there will be a need to determine critical values, p-values, and so forth. When we do a chi-square test, we enter degrees of freedom based upon a probability value or p-value, and then calculate a critical value. Now you could go to the very last tab, and you will see a table for finding critical chi-square values. This table looks very much like a table that you can find in the back of your textbook, where you look up the alpha level in the columns, the most common being 0.05, or 0.01, and then you find your degrees of freedom and where those intersect. Let's say we have 2 degrees of freedom. At a 0.05 alpha level, the chi-square value, or rather the critical value, is 5.991. So if we have 8 degrees of freedom at a 0.01 level, it's at 20.090. You could look up any alpha level and degrees of freedom to find this in a table. It's a pretty common way of doing it. Or, let's go back to critical values. We could just enter 2 degrees of freedom, and there's our 5.991. And if we enter 8 degrees of freedom at a alpha value of 0.01, we get our 20.090. So we are now able to calculate critical values just by entering the degrees of freedom. Let's make it, 12. And make sure our critical value, our alpha is 0.05. You can look up any critical value that way. It just saves you a lot of time. If you have a chi-square value in the degrees of freedom, you can calculate the probability of that particular outcome. So in some of the questions that are on the assignments, it's like, what is the probability for this? Well, enter your chi-square value in your degrees of freedom. You can look up that probability value. I have others for degrees of freedom or the phi effect size. Now the rest of these tabs, the ones in gray, are all different permutations of the chi-square test. This one is a 1/2, where we just have an x and a y value, so you can just enter those. Let's make, so we have 15 people in one group, and 23 people in a second group, and there's our chi-square values and our degrees of freedom and probability and so forth. So we have a 1/2 setup, a 1/3 setup, 1/4, and then the one in red is a 2/2. Now the reason it's in red is because a 2/2 setup is a special case of a chi-square or one of these cross-tabulation tables. Let's say we have, just to keep it simple, we'll say we have male and female, and we have yes and no. All right, so now we need some numbers. So hey, there's 4 of you. I need a random number, a number between 1 and 100. So just give me a number. 100. Okay. 5. Okay. 22 and 61. 614, 61. All right, so there's our chi-square. So we get our chi-square result. which in this case is a 96.126. That's huge. With 1 degree of freedom, probability is tiny. So we could take that up to more decimal places if we really needed to. Critical value is a 3.841. There is a correction factor that we can use in a chi-square. And actually, this is a really good example. You see how in this female yes category we have 5. And when you get values of 5 or lower, it can kind of mess with your chi-square a little bit. In fact, this way we see a tremendous change. A chi-square of 96 drops to a chi-square of 52. Now, if we were to change this 5, let's make it a 35. So now we see a chi-square of 47.192. We still have a continuity correction of a 28. So what I want you to see from this is that we can enter data, and then we just get the results off to the side. What are the expected values? They're right over here. And this is almost like cheating. Results. Your chi-square test is significant. For effect sizes, with many of these, like a 2x4, we're going to be using an effect size called a Kramer's V. It's a very common effect size to be using with chi-square. But, as I mentioned, this 2x2 is a special case. So we use what is called a phi, PHI, for the effect size. And then this would then also allow us to do things like calculating risk ratios or odds ratios. So the odds ratios, right here, that's 7.922, we'll round it up to an 8. So 8 times more likely to say yes than to say no. So you notice how when I put the names like male, female, yes, no, those actually show up in these bar charts below. The legend might actually be compressed. So if you just drag that to the right, there's our yes and no. You see our groups more clearly. So we can see our comparisons. So if I were to ask you which group is really driving this chi-square, you could look into this set of column proportions and say, oh, look at that. That's that bar right there, which is what yes and male. That bar accounts for a great deal of the variability within this data set. Or if we look at the row proportions, we can see that the pattern for the pattern for yes is the inverse of the pattern for no. So we have both column proportions and row proportions. It just depends upon what type of setup you're doing as to which of those two bar charts would be more important to you. So what does this have to do with our examples that we'll be doing in class this week? So here I have some example data. And for the assignments this week, you have one Excel spreadsheet with 3 tabs. I thought that made a lot more sense than posting multiple Excel spreadsheets. You can post one Excel spreadsheet and the data will be on multiple tabs in that single spreadsheet. All right, for this, we have groups and responses. Groups 1, 2, and 3. And here's our numbers for these types of responses. So here's what you would do. I would just start flipping through in this chi-square calculator and find one that matches. And it would be the 2x3. So we can see there's 2x4, or 3x2. Just find the one that matches the layout of the data that you're working with. So I would pull up my example data. And you don't need anything more than just the data points. So I would select all of those and I would copy. Remember, we have yes and no and then groups 1, 2, and 3. Now I'd go back to the chi-square calculator and I would paste. Those groups were 1, 2, and 3, and the answers were yes and no. Okay, so here's my chi-square results. It's an 8.39. The critical value is a 5.99, so I can tell my chi-square exceeds my critical value. My probability is 0.015, which is less than 0.05. That's our typical cutoff score. Degrees of freedom is 2. Kramer's V is 1.06. Chi-square is statistically significant. And as I scroll down, I can see the proportions for either yes and no, or groups 1, 2, and 3.
So if your chi-square is bigger than your critical value, then it's significant?
Then it is significant. So if your chi-square exceeds or is larger than your critical value, then the test is statistically significant. And if you ever have any questions, just look right there where it says your results are. There it is. Now, what would happen if instead of doing our chi-square at like a 0.05, what if we were using a 0.01? Well, that's no problem. Just go to this alpha box and say, I need to do a test at a 0.01. And you'll notice the critical value changes. And oh, now my chi-square test is not significant. So you can update the table and then you will get the results. So I do want you to have the experience of using Excel to create a few of these. But wow, I find this to be a whole lot simpler in its use than just trying to do everything over and over again with Excel. I also want to point out the next to last tab, which is an interpretation tab. I mentioned Kramer's V and phi as measures of effect size. So what are those and what do they mean? You will be reporting on the Kramer's V, but you need to know what that actually is referring to. So let's go back to our 2x3. Our effect size is a 106. So 106, that would be right here. It'd be a very weak relationship. Not generally acceptable is the comment on that. You can then interpret any Kramer's V or phi that you calculate. We had some other very large chi-square values earlier. Let's see where I put them. I think I did the 2x2. So the phi here is a 0.359. Let's interpret that. 0.359 would be in the very strong range. Now notice how the interpretations in the black are really the more, that's what you want. If it's too weak, well, we don't have a relationship. But notice how if we get above that 0.4, we move from very strong to curiously strong. It's either there's a really strong relationship, or more likely what's happening is that we're measuring the same construct or concept. And so really what we have are redundant predictors, or they're really telling you exactly the same thing. If the level of association were to go to a perfect 1, it would be a perfect relationship. And the interpretation of that is that if you know the independent variable, you can perfectly predict the dependent variable. Now this interpretation makes a lot more sense when we put this in terms of a correlational coefficient. But that's, which is essentially what they're mimicking here with the Kramer's V. So this is a value that runs from 0 to 1, but we're looking for that sweet spot in the middle of a certain level of predictive ability, but we don't want it to be too strong or too weak. So what you will do this week is work through, there's several sections for the chapter in the book, and just go through them section by section. There's some extra videos, there's how to do this, there's instructions and so forth. But then at the very bottom of the page, we have assignments for this week. As you do the assignments, there will be 2 that you can do by clicking on the link. It takes you to the Cengage site and you can just answer those. And each of those has videos associated with them, and you can check your answers. So you can find out how to do this. You can watch the video. It uses different numbers, but the same setup. So you can learn how to do it. And if you get something wrong, go back and rewatch the video, or look for this place where something went awry and you can fix that. And then you return to the answers. So you get to check your answers, and you have multiple chances to get it right. So there'll be 2 assignments like that. The third assignment will be the one where you have one Excel spreadsheet with 3 tabs, so 3 different data sets. There is an answer sheet that goes along with that. You can also use this calculator, this chi-square calculator. So grab the data, just do what I've shown you here in this example. And when you've done that, you can write down the results that you find on that answer sheet. And then, once you've done all of that, you would then click on the actual number 3 assignment, and that's where you would enter those numbers, and it gets graded for you automatically and goes into your grade book. So the only thing on the Blackboard part of the assignment is those responses, those answers. You wouldn't need to go out to Cengage for that, and you don't need to know any other, there's no like true, false, or multiple choice questions like that. Just recording their findings. So with that, do you have any questions about what we're doing this week?
Is that due Sunday?
Yes, it is due Sunday night. And you notice, so Unit 1, weeks 1 through 4, not available any longer. We've finished up with that, and we're focused fully on Unit 2, which is weeks 5, 6, 7, and 8. And then we'll have the test at the end of that, and then fortune back is the end of week 9, and that would be due, and then that goes away, and so we're just continuing to move forward with each of the new units as they arrive. Okay. Any other questions about this week or what we're doing? Well, in that case, thank you for being here. Had a good time. Good to see you guys again. Please be safe, be healthy, and I will see you next week.